Okay, so I want to end with a definition, and then after this video, another example of this definition of a way that it's going to be easier for us to imagine what these large three-dimensional functions are going to look like. Because, I mean, certainly if we're going to talk about something like a cone or a sphere or a paraboloid even or a plane, these are things we can imagine and things we can graph. But, I mean, it's very uncommon that I would even have something I could graph, right? I mean, I might have a function like f of xy is equal to e to the xy, for example. There's no way that I'm going to be able to sit down and graph this without plotting points or doing something completely different. And so I want to talk about level curves and contour maps. Before I do that, let me maybe just show you that you've seen this sort of thing before. So here is a map of Lonesome Mountain. And my question is, what do the lines on this map represent? So you may recognize this as something from, you may have learned in elementary school or in high school. I think I learned it in high school, what a topographical map was. So a topographical map is something that tells me where the height changes, right? What is the elevation at some certain point? And so it might be hard to see, but for example, if I highlight it for you, this curve here is 500-foot elevation. And this curve here on the outside is 4,500-foot elevation. And I just realized I've left a 0 out of there. So what this tells us at each level is an elevation, right? And so these are all heights. These are like slices of the mountain. And from this, we can sort of like extrapolate what the mountain might look like, right? So it might look something like, right, we've got some circle and some bigger circle. And so the mountain might look something like this. Right? It gives us a sense for if we can fill in the dots, the mountain might look something like this. So let me, maybe in a different color, draw these curves. So the mountain might look something like this. All right. It's a way to graph something in 3 dimensions. It's a way to tell us what this mountain looks like in 3 dimensions without something like Google Maps or some sort of augmented reality where we can actually look at the mountain. It's a way for us to graph it in 2 dimensions. And so this is something actually we're going to use here in multivariable calculus too. So given a function z equals f of xy, the level curves are the curves obtained by setting z equals to c. So for example, the level curves are these things here. They're living in 3 space, and they're when I set z equal, so for example, this is must be z equals 20, and this is z equals 25, and each of these represents a height, right? So this is z equals 20, this is z equals 25, this is z equals 30, and so on. And so, I mean, these are level curves up in space. If I project these down to the plane, projection of level curves to the plane, then I get something like a topographical map. And so this will, without having to graph something in 3 dimensions, I get a sense for what this must look like, right? I can sort of extrapolate out. I can extrude this up and see what it looks like in 3 dimensions. It's really just a way for us to figure out what this looks like in 3 dimensions. When I draw a contour map, notice these are all at regular intervals. So I have k equals 20, k equals 25, 30, 35, 40, 45. Making them regular intervals gives me a better sense for what things are look like. If I had, you know, at z equals 20 and then z equals 25 and then z equals 40, then it doesn't give me a sense for what's going on here. And in the next slide, maybe I'll try to make it more obvious what I'm talking about here.